Okay, in this video, the last on the full range Fourier series expansion, we're going to look at this example here. We are hoping that you have already had a go at this example, as we recommended that you have a go at it in part 2. So for this example, we want to make a sketch of its periodic extension. Want to determine whether the extension is even, odd, or neither, and then want to find the Fourier expansion of this. If you haven't, you can still pause the video and have a go at the example before you compare with our solution. All right, so we have got f of x equals to 2x minus x squared. So first thing I want to do is to make a sketch of this. This is a parabola. X squared is negative, so it's facing downwards. Upon factorization, you can see that there are going to be two roots of this, one at 0 and the other one at 2. So what it means is that we're going to have a shape that looks like something like that, and so that is our period. So in terms of the framework, our period 2L is equal to 2, so that means L is equal to 1. In terms of the periodic extension, that means on the right hand side of this, on an interval of 2, so that means from 2 to 4, we're going to reproduce exactly the same shape, and then 4 to 6, exactly the same shape. On the left hand side, 0 to negative 2, exactly the same shape. So this is the picture that we are going to have. So that is the periodic extension of this function. Is it even, odd, or neither? Well, we say it for even functions. The function is going to be a symmetric about the vertical axis. Well, we see this one is indeed symmetric about this axis. If you do a mirror reflection of this, you get this one. Reflection of this one is this one, etc. So this function, the periodic extension, is even. So periodic extension of f of x is even. Notice that, this doesn't mean that f is even as the periodic extension. This function on its own, it's neither even nor odd, because this function is going to look something like this. So on its own, it's neither even nor odd, but we're talking about periodic extension of it. It's going to be even. Now, when it comes to the Fourier series, the sine terms are odd and the cosine terms are even. Okay, so if the periodic extension of the function is odd, for instance, then you don't expect any cosine terms in the Fourier series. However, if the periodic extension of the function is even, as we have determined for the function that we're talking about, then this implies that we cannot have any sine terms, because you cannot use odd functions to build an even function. So this one, straight away from there, we can imply that Bn is going to be equal to 0 without having to do a calculation. Okay, so when it comes to part C, we're just going to work out the values of the ANs. And if you are doing a test and exam on this, you're going to get the same amount of marks whether you use this fact and then just state that Bn is going to be 0 correctly, of course, or if you go through the whole calculation after a page or two and then find that Bn is equal to 0. So, and this is also going to have a bearing in the next segment of Fourier series, which is called the half-range cosine and the half-range sine series. So the fact that a function is, or rather the ability to determine if an extension of a function is even or odd is very important there as well. All right, so let's start with the AN then. So we've determined that L is 1, so it's going to be 1 over 1. If we take x naught to be 0, then x naught plus 2L is going to be 2. It's always advisable just to use the interval of the function given, which is 0 to 2 here, when doing your calculations. We could want to use 2 to 4, but then we'd have to find the functional form of the this parabola here, which is going to be this one shifted to the right by 2. Okay, so it's going to be more complicated, or we could use this one, but then again, okay, probably that one is going to be easier from this one if we just twist this around. So the equation of that one would be actually that is still wrong, because this one is going to be facing upwards. But bottom line is just use the interval of the function used, and then that is going to be your f. So this time we are going to have 2x minus x squared dx from 0 to 2. Integrating this is going to give us x squared minus x cubed over 3 from 0 to 2. Plugging in and working this out going to give us 4/3. Then for values of n, so that was a naught. For values of n 1 and bigger, so we're going to have the integral from 0 to 2, 2x minus x squared. This is going to be cosine n pi x over L, but L is 1, so it's just going to be n pi x. Then again, we've got a polynomial here times a trigonometric function cosine, so we're going to use integration by tabular technique. So that's going to be 2 minus 2x. We differentiate these ones, minus 2 there. The last one is going to be 0. So we've got cosine n pi x here. Next one is going to be 1 over n pi sine n pi x. Then minus 1 over n squared pi squared cosine n pi x. And the last one is going to be negative 1 over n cubed pi cubed. This one is going to be sine n pi x. Okay, then we match these up. First one is plus, minus, and then plus. So our AN is going to be equal to 2x minus x squared over n pi sine n pi x plus 2 minus 2x over n squared cosine n pi x, and then the last one is going to be plus as well, 2 over n cubed pi cubed sine n pi x. Okay, then this is from 0 to 2. So let's just talk about what's going to happen here. So if you plug in x is 2, this is going to be 2n pi, which is going to give us 0. This is going to be 2n pi, cosine 2n pi is 1, but this is going to give us negative 2. This is going to be sine 2n pi, which is 0 again. So it's just going to be this term here. 2 minus 4 is going to be negative 2 over n squared pi squared cosine 2n pi. Then when we plug in x is 0, so again when x is 0, this term is going to be 0. This is going to be sine 0 anyway. This one is going to be cosine 0. This is going to be 2, but remember we're subtracting now, so it's going to be minus 2 over n squared pi squared cosine 0. Then when we plug in 0 here, that's going to be 0. So these are the only two terms that are going to survive, and these two terms add up. So these two terms add up to negative 4 over n squared pi squared, and so that is going to be our an. So n should not be equal to 0 here because we're dividing by n, and we've already sorted that one out there because we've worked out a naught. So we are now in a position to write out our final expression of the Fourier series of this. Is going to be a naught over 2. So a naught is 4/3, a naught over 2 is that. Then there's going to be minus 4 over pi squared. So that's just this negative 4 over pi squared. And then the n squared is going to go with each of the terms inside the brackets. For n equals to 1, it's going to be cosine. Remember, we've got n pi x, so it's going to be cosine pi x over 1. Then we're going to have cosine 2 pi x over 2 squared. Then we're going to have cosine 3 pi x over 3 squared, etc., etc. We can write this in closed form. It's going to look something like this: cosine n pi x all over n squared, n ranging from 1 to infinity. So that's just this going with that there. All right, and so that is the end of that. In the next sequence of videos, we're going to look at the half range sine and cosine series, and the work we've done here is going to be important, of course. Thank you for watching. Do, of course, press the subscribe button and like the video, and thank you.